Okay, good morning, dear students. So we're going to be talking today a little bit about light. And you see up on the board right there, you've got what should be a fairly simple, easy question, right? What is light? But when you actually try and put words to it, it may not be quite so easy. What I'd like you to do is on that paper that's back there, take about 2 minutes, maybe less, and try to give me a good definition for what light is, or what causes light. You have my permission to be totally dead wrong. Want to hear what you think, and we'll see what nuggets of truth we can pull. McKenna, what do you think light is?
A source of energy that makes things not dark.
A source of energy that makes things not dark. I like the fact that you use energy in there. That's excellent. Okay. Shiloh, what is light? Energy that shines in beams. Now, what do you mean by shines in beams?
Yeah.
So the way it moves is okay. I mean, the beams do this. What do beams do? More or less straight lines. Okay, it can move in straight lines. Erica, what's light?
Okay, my one is light is caused by energy which can be reflected.
Okay, it is caused by energy. It can be reflected. I like that. Okay. Emily, what do you think light is?
A source of energy that provides brightness and can be caused by a chemical reaction.
Okay. Chemical reactions can sometimes cause light. Other things besides chemical reactions can also cause light, right? Okay. Not bad. Energy is involved. I like that we keep hearing that. Reed King, what is light?
A form of energy that is given off in some chemical reactions, and it reflects off surfaces and always travels in a straight line.
Okay, so you basically stole from everybody. That's good. Yes, you're right on all those counts. Still quite doesn't get to what exactly is causing that light, though. Okay, we'll see if we can get any closer. Avis, what's light?
Is an energy that produces things that allow us to see better.
Okay, it produces things that allow us to see better. It does produce things. Okay, and we'll put a name to those things here before we're done. All right. Haley Jones, what's light?
Light is rays that brighten up the universe.
Light is rays that brighten up the universe. That sounds like a greeting card, but I like it. Okay, that works. And last but not least, Samantha, what is light? It's a form of energy. Okay. So you've all hit on, yes, that light is a form of energy, which means that it's not matter, right? It does not have mass, it does not take up space, but it is a form of energy. When you get right down to what light is, though, here's what light is, okay? So be ready to write this down. Here's the best definition for light you're ever going to hear. Light comes from falling electrons. And that should immediately have you asking all kinds of questions. It's like, why are these electrons falling? Where are they falling from? Where are they falling to? Can an electron really fall? What's pulling it down? What's pulling it anywhere? So, instead of thinking in terms of electrons, which you can't see, I'm going to paint you a word picture, which I know each and every one of you will have no problem seeing in your mind's eye. Imagine you have a birthday party for a whole bunch of tiny kids, and there's lots of cake, there's lots of Kool-Aid, and there's a trampoline. Have you got a picture in your head? You know exactly how the story plays out, right? Kids get the cake and the Kool-Aid. What happens to the kids?
They get sugary.
They get all energetic, right? And then you're like, hey, look, a trampoline. And what do they do? They run to the trampoline and they bounce, and they hit the trampoline, they bounce up in the air, and then they just stay there forever, right? They fall back down. Now, are they doing this in silence?
Screaming.
It's noisy, right? What does it sound like? Make the noise. Wow, what boring kid you know. Okay? So, if these are your electrons, when they are falling from where they have jumped to, they are screaming, right? They're going, ah! Something like that. Folks? light is literally screams being given off by falling electrons. I'd write that down because that's some good stuff. But wait, King, I didn't know that they screamed. Well, they can't scream where you can hear them. But you can see their screams. Now that still doesn't answer the question, where are they falling from and where are they falling to? So, on this next slide, let's consider a typical atom. Okay? Now you already have learned, either from conversation or from video clips, that electrons tend to reside outside the nucleus, and they tend to reside at certain distances from the nucleus, called energy levels. Okay? And that's where they are the most stable. So if we have a nucleus, let's put a couple protons, a couple neutrons in here. Does that work for your nucleus?
Yeah.
Okay, what element is this?
Helium.
It's helium. It's got 2 protons, atomic number is 2. Which means it also has 2 electrons. And these 2 electrons will be on one of those energy levels, or at one of those distances from the nucleus. Now, electrons tend to get as close to the nucleus as possible. Can anyone guess why?
Opposite attract.
Opposites attract. And what's attracting them?
Like protons.
The protons in the nucleus with their positive charges are attracting those electrons to them. Now, think back to junior high or whenever it was that you talked about potential and kinetic energy. I have these 2 markers, right? Which one of these markers has more potential energy? The blue one or the red one?
Same
The blue.
The blue one. Why? It has farther it can fall. In this case, we're talking about gravitational potential energy because gravity is accelerating both of these downward, right? In this case, it's not gravity that tends to pull them in close. It is that opposite electrical charge that pulls them in close. But here's what happens to these atoms. Energy is going to come in from somewhere, and that could be energy caused by electricity, could be energy caused by heat, or any number of other things. But this energy is going to come in, it's going to hit these atoms, and it's going to get absorbed by an electron. That electron is going to do just like the kindergartner with cupcakes and the red Kool-Aid. It's going to get all excited, and it's going to, boing, jump up to a higher energy level. So it's going to absorb that energy, but just like the kid in the air, it's not going to stay there, and so it's going to fall. Oh! As it falls, it's going to scream, and the scream it gives off is going to be a little packet of light called a photon. Make sense?
Yeah.
Okay? You were saying it gives off thingies of light? Yes, those are the thingies that are called photons. This other electron over here is going to also absorb some energy. And it's going to get all excited. Whoa! It's going to jump all the way up there! When it jumps all the way up there, it might fall back down a little, or it might fall all the way back down. When it falls all the way back down, it's going to scream, and it's going to give off this much energy, also as a photon. Now, depending on how far it falls, it's going to give off different kinds of streams. And in the case of photons, they're going to have different amounts of energy, and they're going to be different colors. This is some good stuff. I'd write some of this down if I were you. So the kind of light given off depends on how far those electrons fall. It also depends greatly on how many electrons are present and where they are falling from and where they are falling to. Now, take a look at the periodic table. How many different arrangements of electrons do you have up there? Give or take. Hundreds, right? About 112 on that chart, about 118 or so that we know of. Which means that no 2 atoms have the same setup of electrons. No 2 atoms are different elements anyway. That also means that the kind of light given off by an element is unique to that element. No two elements give off the same kind of light. And you can use the kind of light that's given off by these falling screaming electrons kind of like a fingerprint to identify what element made it. Here's a few of them now. So when you take a look at that, there's lots of observations you could make here. Make one for me.
The lower is like more green and black. The higher is more just red and top.
Okay.
More
So
lines.
you can see, check it out. Toward this end of things, they tend to be more toward the red, and toward this end of things, they're toward the blue and the purple, right? Okay. So you're seeing different colors in different positions. Do each of these elements have the same number of little spikes? No. And are the spikes in the same positions? No. This yellow here on rubidium is in a different place than this yellow here on cesium or this yellow here on sodium. Okay? Now, it would be really great if we had some way of actually doing a lab in here where you could actually look through an instrument and look at the light source and actually see this. Now, that'd be cool, right? You know, it really is a shame that, you know, we don't have something. If we did, it would look, you know, something kind of like this. Okay. And the way you use it is you would take it and you would look through the little end and point the big end at, you know, like a light. You'd be able to see a little spectrum of light and a little pattern of colored lines like this. Okay. So it would show up what you'd actually be seeing inside there would look like. You'd see a little ruler with some numbers on it. You'd see a little pattern of lines going through there. And it's really a shame that I don't have enough for everybody in the class to borrow one and have their own book through. That would be awesome if I did 1, 2, 3, 4, 5, 6, 7, 8. So what I would like you to do is I would like for you to practice using these spectroscopes. Look through the narrow end, point it at some kind of light source. I wouldn't point it at the board, point it at one of these lights that's up here in the ceiling. And what you should see, when I look through here, is I kind of see a big smear of color over by the numbers, but I see really strong bright lines. I see a really strong bright reddish one, close to the 6. See a really strong bright greenish one, and then further down I see a strong purplish one that's down between the 4 and the 5. Are y'all seeing what I'm seeing? And if you can't see it on a light that's closer to you, look at one that's further away, maybe further back in the lab. That'll be a little bit easier to see. Now set these down for just a minute, and let's talk about why it's doing what it's doing. Okay? We've got a simulation here, and in our simulation here in the middle, I've got a single atom of hydrogen. We're going to hit it with some energy. Boom. Anytime. It would be great. Boom. You can do it. Maybe. Maybe not. Maybe I broke it. Oh, maybe I can. Right. Here we go. So now check it out. It hits it hits that atom. Over here on the right side, you see here's the lowest energy level close to the nucleus. Here's some of the higher energy levels. Let me put it in slow motion and watch what happens here. Okay. Here comes some energy. It's coming in. Boom! It makes the electron jump up, and then it screams. It screams that much. Then it gives off a photon. Now that photon right there is actually not one you'd be able to see. That's ultraviolet. Okay? It's got way more energy than you can actually see. So I'm going to turn on our spectrometer here. Instead of doing just one, I'm going to put it on continuous, and I'm going to take it out of slow motion. And I'm going to crank up how much energy we're getting through it. Turn this sucker up. Now, we're starting to get a few different kinds here, right? We're seeing some big purple ones. Let's see if we see anything else. Oh,
Red.
there's some little red ones. Those are actually infrared. They're not visible to us. Some more purple. Anything else? Now, we're getting lots and lots of these little purples here, and we're getting kind of a purple spike down here on our spectroscope. I wonder what would happen if instead of just one atom, we had a whole bunch of atoms. Let's crank it up here. And we can see what's going on. Oh, it's getting real crazy up there. Well, I see some big red glowing things. I see some purples and some blues. And I'm beginning to see a red spike on my spectrometer. I'm beginning to see my purple, which is really strong, and also a blue. Oh, there's kind of a turquoisey green. And so this right here would be the spectrum that I would see coming off of excited hydrogen. Okay? Coming off of those little hydrogen electrons that are falling down and screaming after they've absorbed energy. I'm going to go ahead and stop the recording.